So the formation of the star, we start with a protostar. What is basically a protostar? It's how the star born, the formation. So what is the interstellar cloud? The interstellar cloud is the cloud which contain like the space, a region is there between the different stars, or a cloud of a gas and a dust that occupy the space between the star. That is called an interstellar cloud. And this interstellar cloud, we have a molecular cloud. What is a molecular cloud? Where we have a molecule of gas and at low temperature, like it's relatively a colder region, you can also say. But we have molecules in this region. Now, what happened? How the formation of a star, like the first phase, happen or occur? So the spaces between the stars is known as the interstellar cloud. And in this interstellar cloud, there are regions where we find molecules and molecules of mainly hydrogen gas. A cold gas is there, cold and dense gas. Dense means, like example, more particles in a unit space, and cold means the temperature is relatively low. As a result, what will happen? These molecules come closer to each other. When these molecules come closer to each other, the gravitational potential energy change to kinetic energy. They move faster. As they move faster, the temperature will increase. When the temperature increase, so it also attract more matter from the surrounding. So it try to attract, or it attract more matter from the interstellar cloud. As a result, as more matter it attract, the gravitational force is there, it start to increase. So there is a gravitational force is there, gravitational pull is there towards the center, and the radiation pressure is there outward. When the radiation pressure and the gravitational forces are balanced with each other, the star will not change the size, and that we call that the protostar is now in a stable state or a stable condition. But once the radiation pressure is higher, the size, so the birth is the protostar. But this protostar becomes stable when the radiation pressure is equals to the gravitational force. But if the radiation pressure is more than the gravitational force, as a result, what will happen? Like outward pressure is more, so size of the star will increase and it will turn into a giant. And opposite can happen if the radiation pressure is less than the gravitational force. So as a result, what will happen? The size will decrease and it will start to turn into a dwarf. And the size of a star mainly depends on the core temperature. If the core temperature increases, the radiation pressure will also increase and the size will increase. If a core temperature, the central core temperature of a star, it decreases, so radiation pressure decrease and the size of the star will also decrease. So that's how the star formation occur, or formation of a star happen. Then it depends on, like, the cycle of a star. After a protostar, what cycle it will follow depends on the mass of a star. We may have like sun-like star, or we may have which are known as a low mass star. Sun-like stars are also known as a low mass star. Or we may have massive stars or the high mass stars. So protostar is the same thing. Like protostar, when the protostar happen, what is the main difference? A low mass star will have a small amount of matter in it, or it will have a smaller protostar. But a high mass star will have a greater size of the protostar, the first phase. So the cycle of the star depends on the initial mass. If it's lighter, like if it's a smaller mass like our sun, then it will have a different cycle as compared to the massive star. Like here, because this part is main, and then we'll move on back to the Hertzsprung and Russell diagram. If we have a protostar, leave this the T-Tauri phase. Just remember, as your level, you just remember you start with a protostar. Leave this part. Just remember a protostar. So example, if you have a protostar and that protostar is having a mass like same like the mass of a sun. Heavy high mass star means like they have about 8 times or more than 8 times the mass of a sun. And the low mass stars are like example 3 times the mass of a sun or same like mass of a sun. So first what will happen, the low mass star, this will form a stable star. The high mass star will also form a stable star, which is known as the main sequence star. When it's in a main sequence star, the star won't change. We will discuss in detail why they have a different size, why their cycles are different. That we'll discuss in detail. But right now we are studying or we are discussing the fact that what cycle it will follow. So it totally depends on the initial mass, the molecular cloud. If it's a low mass star, then it will be a stable star, then stable star turn into a red giant, and then planetary nebula, white dwarf, or a black dwarf. But if it's a high mass star, it will turn into red giant, then there will be a supernova and turn into a neutron star and a black hole. But how these cycles, what happen in these cycles? This is for a low mass star. First, what happened? So this is the low mass star like sun-like stars. So first, what happened? The stars start as an interstellar cloud, as we discussed. What is the meaning of interstellar cloud? Interstellar cloud means like the cloud between the stars which contain gas and dust. That's called interstellar cloud. And that interstellar cloud, the part of that which is a molecular cloud which contain mostly molecule. So due to the gravitational force, the cloud, the interstellar cloud contract very slowly, and it gets dense enough to form a protostar. So first, like things were scattered. In an interstellar cloud, all the things are scattered, spread out. But as these are coming closer to each other, the size start to increase, it become more dense, and what it turned into a protostar. Then eventually what happened, the concentration of the atom increases, like there will be more particles, more atoms in a unit space, and that is enough to increase the temperature of the center of the protostar. Like there are surrounding as well, but inside, like the center core, the temperatures start to increase as the particle come closer. Their potential energy change to kinetic energy. They move faster. As a result, the temperature increases. And at the center of a protostar, it start a fusion of a hydrogen nucleus. So mostly like molecular cloud, the hydrogen from the molecular cloud start to fuse together and it turn into helium. And this release the energy and create enough pressure to stop the gravitational collapse. Means due to the nuclear fusion, there is a radiation pressure outward. And that radiation pressure balances with the gravitational force. Because of mass, there will be a gravitational force. So that radiation pressure balances with the radiation pressure balances with the gravitational force, and it will stop the star from changing the size, and that star is known as the main sequence star. So the low mass star basically is the cycle of our sun. So right now our sun is a main after a protostar it enter a main sequence star, and when it is a main sequence star it does not change its size. So our sun is a main sequence star of a low mass stars or category. Then what will happen when the hydrogen fuel ceases? Like the hydrogen fuel, because it undergo hydrogen fusion. So hydrogen fusion is like it's stopped or slowed down. Then the outward pressure falls because the outward pressure is due to the radiation or due to a nuclear fusion. So then it start to decrease. As the outward pressure start to decrease, what will happen? If the outward pressure start to decrease, it means the gravity is more or gravity is strong. At that point, the stars start to contract. The size of a star decreases. So right now, our sun, which is a main sequence star, when it used up all the hydrogen, the size of the sun will decrease or it will shrink. When the size of the sun will decrease or it will shrink, the temperature of a core increases too much, and as a result, it will start a helium fusion. So first, it was a protostar, then it become a main sequence star, and then as a result, when it hydrogen fusion decreases or slow down, the radiation pressure decrease, so gravity is stronger. It reduces the size of the core. As a result, when the size of the core decreases, the temperature start to increase, and that temperature is sufficient or it is enough to undergo a helium fusion. And that helium fusion release enormous amount of energy or too much energy outward. So as a result, now the outward pressure will be more than the gravity. So when the outward pressure is more than the gravity, the size of our sun will increase and it will turn into a red giant. Yeah, helium will form. Yeah, it's a cycle. Like hydrogen form helium, helium will form like carbon, nitrogen, and so on. So then our sun will be red giant. And when it will be a red giant, like the size of a sun, like we have a Mercury and Venus, it will be sufficient to cover up the size of these two planets as well, like the orbits of these planets. It will be a red giant. So our sun is a main sequence star right now. Once the hydrogen is used up, the size of our sun will decrease. When the size decrease, the core temperature will increase and the nuclear fusion of a helium increase, and that produces too much energy, which increases the size of a sun. When the helium fusion ceases, like when the helium fusion start to decrease, so now the outward pressure is no longer balanced with the gravitational force and it will contract again. So there are two ways it will contract. One is when hydrogen fusion decrease, it will contract. The second one, when the helium fusion decrease, it will also contract. So it will start to contract because the helium fusion start to cease or decreases. I said the size of a sun will increase too much that it will take the orbit of Mercury and Venus when it be a red giant. So as a result, what will happen for our so this is our sun. Right now it's a main sequence star. Then what will happen? The size of the sun will decrease. Why the size of the sun like it will decrease? What will be the reason for that? The reason is because the hydrogen fusion ceases or the hydrogen fusion decrease. That's why the size will decrease. Then the helium fusion start. When the helium fusion start, this radiation pressure will be higher than the gravitational force. So the size of a sun will increase and it will cover the orbit of Mercury and Venus. So the temperature of the surrounding or Earth may not be able to support the life when the sun is in a red giant phase, and that is a red giant because the temperature will be so high on Earth. Even that is enough to evaporate all the water. Then what will happen when the helium fuel, as it sees the pressure, the outward pressure is no longer balanced with the gravitational force. And this time the temperature of a star during a contraction won't rise too much or will not cause too much fusion, because to do hydrogen fusion we need low temperature relatively. To do helium fusion we need high temperature. To do a fusion of a heavy atoms. Like first it was started with hydrogen, so we need relatively low temperature. Then it turned to helium, we need relatively high. Then it will be carbon, we need a very high temperature. So when the star is collapsing, this temperature is not sufficient to undergo further fusion. And as a result, what will happen? So the time, the temperature, the star in this contraction won't increase too much to gas fusion. And after certain contraction, the outer layer of a star become unstable and it is ejected into a space as a planetary nebula. Like what will happen? Because say, if I draw, first we are talking about a low mass star. The high mass star have different cycle. Say this is an interstellar cloud. Then apart from this interstellar cloud, there will be a molecular cloud where we have a cold gas. Initially, there is a cold gas and dense as well, like more particles are there. And this cold or dense gas, the particles come closer to each other. When these particles come closer to each other, it heats up. When it heats up, it undergo a fusion between hydrogen. When it undergo a fusion between hydrogen, this, this is a protostar. When it undergo a fusion between hydrogen, the radiation pressure, which is the outward pressure, balances with the inward pressure and it enter a main sequence star. Once it reach a main sequence star and the core it will not change its shape or size, then the hydrogen fusion decreases because the amount of hydrogen is decreasing. So as a result, when hydrogen fusion ceases or decreases, then again it will change its size because the gravity is stronger than the radiation pressure. Radiation pressure is outward, but gravity is stronger than a radiation pressure, so size decrease. As a result of this decrease in size, the temperature of the core will increase, and this temperature is sufficient to start the helium fusion because most of the hydrogen here has converted into helium because of a nuclear fusion. And this helium fusion, when it happened, the pressure, outward pressure suddenly increases. Not sudden, it's a phase there. But as the outward pressure increase, the size of a star will increase. So the size of a star will increase and it will turn into a red giant. So first we were having a protostar, then we were having a main sequence star, then we have a red giant. When it's a red giant, why? Because the radiation pressure is higher than the, due to helium fusion, radiation pressure is much higher than the gravitational force, gravitation to cause a gravitational collapse. Once the helium fusion used up, again it will contract. And when it is contracting, this time the temperature is not sufficient to undergo fusion of other element. So this star will lose the surrounding because there are always the matter is there in the surrounding of a star. So it will lose its matter in the surrounding matter, which is there. It will lose that. And what we call that? We call that as a planetary nebula. So all the matter is going out and only the core is left behind. So core is there, every part, the core is there. But what happened? Now it's not able to hold these particles. So they are going out in the surrounding and the core is left behind. So what we call this phase, we call that as a planetary nebula. The elements in the core will cool, and as a result, when this core will cool down, what it will turn into? It will turn into a dwarf, and that is called a white dwarf. So first we have a protostar, then a main sequence star, then we have a red giant, and then a planetary nebula that turned into a white dwarf. As you can see here, when we start with a low mass star like sun-like star. So this is a protostar, then it's a main sequence star, then our sun will be a red giant, then a planetary nebula like core will be left behind, and all the matter is spread in the surrounding. And the central core, which is left behind, start to cool down. It turn into a white dwarf. And then the white dwarf will turn into A black dwarf, how the white dwarf turned into a black dwarf, it's like it's like a cool down stage. Is it clear? The cycle of the low mass star. Anyone having a question or a doubt in this?
No, sir, clear.
So star cycle of the massive stars. Massive stars means like they have mass like 8 times or more than 8 times the mass of a sun. So massive stars have lot of fuel. Like basically the size of a protostar decide what will be the cycle. Because if lot of interstellar clouds are available nearby, so it will be a massive star. If you like less mass is available nearby, then it will be a sun-like star or a low mass star. So what happened? They have a lot of fuel and they use up hydrogen at a greater rate because the temperature is high. For the high mass star, in a protostar, the temperature is much higher than a low mass star. So hydrogen fusion happen very fast, and as a result, they have a shorter lifespan than low mass star. So high mass star used up hydrogen fusion quickly as compared to low mass star, because low mass star have a low temperature relatively, so the fusion happen at a slower rate. But for high mass star, the temperature of a core is so high, as a result the hydrogen fusion, it release energy per second, energy will be more as there are more fusion every second. So unlike the low mass star, the massive star can continue a fusion reaction until it's mostly iron. So the same idea, the low mass star, first it started with hydrogen, turned into helium. Then helium turned into other elements such as carbon. But for high mass star, they can, like carbon can turn into silicon, silicon can turn into iron. So they can produce heavy elements. How is temperature high here? The reason is that because the low mass star started with a smaller interstellar, like less amount of interstellar cloud, the dust and the molecules. But the high mass star started with a greater number of the particle. So when these particles will come towards the center, like example, this is representing a core, and this is representing a core. So here what happened, and the particles will move, like they will have a greater change in the potential energy as they will move towards the core. So kinetic, and if the potential energy decrease more, kinetic energy will be higher. If a kinetic energy is higher, the temperature of the core will be high. Here what happened, a smaller distance they move towards the core compared to, so this is a high mass star, this one is a low mass star. So in a low mass star, they move relatively shorter distance, like smaller potential energy change. So kinetic energy will be higher, but not like kinetic energy will increase, but not with a greater rate as compared to a high mass star. So the temperature will increase, but relatively low temperature compared to the high mass star. The energy is always conserved. So as a result, what will happen as they undergo a fusion, after that it can no longer undergo a fusion, a nuclear fusion, and it stop producing energy. Why the energy is conserved? Because there is no air resistance, no friction. That's why the energy is conserved here. So after it undergo, there is no longer a fusion reaction. It stop producing energy. And this happened even abruptly than a low mass star. As the energy is conserved, the potential energy changes to kinetic energy. Due to this kinetic energy, the particles move faster and it undergo a fusion. And as the temperature is very high, it can undergo a fusion for heavy elements as well, compared to a low mass star. And as a result, what will happen when all the things come closer to each other, it will collapse and undergo incredible collapse and bounce back. Like it's like all the particles, its collapse is so strong Then all the particles are like bang with each other. As a result, when they bang with each other, that will produce an explosion, which we also call a supernova. And this supernova, the light from a supernova can even outshine the entire galaxy. Like it's too much light that what we see a light, observe a light from supernova that can outshine the whole galaxy. And after a high mass star explode, the entire mass has completely shattered. A whole star is completely shattered, and it will turn into a neutron star or a black hole. Like I'll show the cycle of the star. So what happened? First, we have started with the protostar, and the protostar will start with a main sequence star. In this main sequence star, what will happen? The hydrogen fusion happen or occur, and the size of a main sequence star for a high mass star will be more than the low mass star. The hydrogen fusion create a radiation pressure which is outward, and there is a gravitational force is there that is inward. The radiation pressure balances with the gravitational force, so the star won't change its size. We call that as a main sequence star. Once the hydrogen fusion used up, the size of a star start to decrease, collapse. And what happened? That caused the temperature to increase. It started like hydrogen fusion, now turned to helium fusion or other heavy element fusion. And this other heavy element fusion, again, what it create an outward pressure. And this outward pressure is more than the gravitational pull. So when this outward pressure is more than the gravitational, like gravity is pulling all the things together towards the core, and the radiation is pushing all the things outward. But the radiation pressure is so high that the size of the star will increase, and it is known as a red supergiant. So in a low mass star, we call that as a red giant, but in a high mass star, we call it red supergiant because it's a bigger in size. Then once all of the fusion occur, like abruptly stop, what happened? The radiation pressure is so high that everything collapse due to this radiation pressure. Like once the radiation pressure decreases, the gravitational force is so high, so things will come closer to each other, bang with each other, and bounce off. And when they bounce off, it will produce an explosion. What we call that explosion, we call that as supernova. So here, how the star death of a star happened by supernova. Here, what happened? The planetary nebula. So that's the difference. Like in a low mass star, it's a planetary nebula. Like it's basically the surface of a star is not able to come towards the core, and that is left in the surrounding. It's called planetary. But in a supernova, it's an explosion which cause. So this explosion which caused most of the matter to, like most of the energy, the matter to escape, and the star will turn into a black hole. What is a black hole? Black hole means, as I mentioned, it will be massive. Too much mass is there in a small space, and it's like so strong gravity that it does not allow the light to escape. So surrounding of this black hole, we'll have an interstellar clouds. So high mass star tend to produce the black hole, and a neutron star means a very small star is there. That is refers to a neutron star. So a collapse star composed almost entirely neutrons only, which form when the star more than the 8 solar masses reaches the end of its life. So these are the terminologies you have to learn. The red supergiant, like they are similar to red giant, but they are formed from the massive star. So similar to red giant, they form when the stars which have at least 8 times the mass of the sun, that's from red giant. Supernova is basically an exploding star that begins the life with more than 8 solar masses, and it run out of a fuel, like it cannot undergo fusion. Neutron stars are like composition of a star, only neutron, and a black hole is a final stage in the life cycle of a star, which started with a high mass star, and it is enough mass left after the explosion that collapsed to a very like small point that it cannot allow the light to escape. So this is the difference between the star cycles. We may have a low mass star, we may have a high mass star. High mass stars usually like 8 or more than 8 times the mass of a sun, and low mass stars are like same like mass of a sun or even 3 times or the mass of a sun. Is it clear? The star cycles. Yeah, black hole is very small
Yes,
but
sir, clear.
dense. The black hole. So you have to memorize these cycles, the stages, learn the definition of each. So a quick review, what like we started with a protostar. If we have a sun-like star, it will be a main sequence star. It will remain there for a longer time as compared to a high mass. It will turn into a red giant, the low mass, the high mass turn into red supergiant. It will produce a planetary nebula, but this will produce supernova. It will turn into a white dwarf, then black dwarfs. This will produce black holes and neutron stars. So what happened inside a black hole? The black hole, the information is limited about a black hole. The reason is that because to examine or to observe something, it should emit out a specific amount of light to identify what is happening. But it does not allow electromagnetic radiation to escape. So from the surrounding, we can identify that this region is having a black hole. From its surrounding, we can tell. So this is a Hertzsprung and Russell diagram, which is showing a relation. Yeah, stored matter in the singularity at a very small point. So this is a main sequence line. Like if a start temperature is high, it will give more light. If a start temperature is low, it will give a smaller amount of light. The black hole does not allow any light to escape from its center even. So the sun, our sun is like a main sequence star, then it will turn into red giant, this region, then it will turn into a white dwarf. This is the cycle which our red giant will follow. This is a Hertzsprung Russell diagram, which shows how the variation, this is a high temperature. On x-axis, it's starting with a high temperature and decreasing at temperature, low temperature. Luminosity means like how much light it emit out. So if a star is having a high temperature, it will be more luminous. But why the white dwarfs, even though they have a high temperature but not too much luminous? Because the white dwarfs, the size is very small. They have high temperature, but size is small. The red giants, they have, even though their temperature is low relatively, but their size is big, that's why they give more light. Yeah, this data is from the information from different stars, known stars. So this was about the star cycles, the low mass and the high mass stars.